When current flows through a solenoid, it creates a magnetic field. This process requires work, and that work is stored as potential energy within the magnetic field itself. Today, we will calculate exactly how much energy is packed into that space. To understand energy density, we first look at the geometry of a standard solenoid. It has a length L, a cross-sectional area A, and a total of n turns. The internal volume where the field is strongest is simply a times L. The ability of the solenoid to store energy depends on its self-inductance. Inductance is a measure of how effectively the device creates magnetic flux for a given current, determined by its physical dimensions and the number of turns. The total magnetic energy stored in an inductor is given by the expression 1/2 L times current squared. This energy is not stored in the wires, but in the magnetic field lines filling the interior of the solenoid. We can relate the current to the magnetic field strength, B. For an ideal solenoid, B equals the permeability of free space times the turn density times the current. This allows us to substitute current out of our energy equation. Energy density, denoted by a lowercase u, represents the amount of energy stored per unit volume. By dividing the total energy U by the total volume V, we find the concentration of energy at any point in space. Let's start the derivation. We substitute the geometric formula for inductance into our energy equation. Notice how the area and length are now explicitly part of the energy expression. Next, we express current in terms of the magnetic field B. Since B is what actually holds the energy, this shift is crucial for finding a field-centric formula for energy density. After simplifying the algebraic terms, we see that the total energy is proportional to the square of the magnetic field and the volume of the solenoid. We are now one step away from our final goal. By dividing by the volume, area times length, we get the energy density, U equals B squared divided by 2 times mu naught. This elegant result shows energy density depends only on the field strength and the medium. Let's try an example. If a solenoid produces a magnetic field of 0.5 Tesla in a vacuum, the energy density is approximately 99,000 joules per cubic meter. That is a significant amount of energy in a small space. Notice the relationship is quadratic. If you double the magnetic field strength, the energy density increases by a factor of 4. This exponential growth is why high-field magnets require such immense structural support. If the solenoid has a core material other than air, we replace the permeability of free space with the material's specific permeability. This can drastically change how much energy is stored within the device. In the real world, this principle is used in MRI machines and particle accelerators. These devices use superconducting solenoids to create massive magnetic fields, storing enormous amounts of energy in relatively small volumes. To summarize, magnetic energy resides in the field itself. The density of this energy is proportional to the square of the magnetic field and inversely proportional to the permeability of the medium. Here is a quick question for you. If we triple the magnetic field strength inside our solenoid, by what factor does the energy density increase? Think about the squared relationship in our formula. The correct answer is 9 times. Because the field strength is squared, tripling B results in 3 squared, or 9 times the energy density. Thank you for learning with us today. Generated by Vision Solve AI.